Scale-up is a fundamental aspect of chemical engineering. Imagine having to build every prototype for a project at its full size. It would be time-consuming and expensive. In other words, inefficient. Researchers use dimensionless groups and scale-up to understand the behavior of large apparatus through the use of small-scale machinery with similar properties. If, for example, an oil pipe was to be designed, it would be difficult to build every prototype of a 3 meter in diameter tube. However, in a lab, a much smaller prototype could be built and, through the use of dimensionless groups, we would be able to understand the adjustments to make on the small pipe to make the transport more efficient. The same changes would then be applied to the larger pipe. Dr. Eduardo García Diego Ortega is a researcher at UCL who will discuss the importance of scale-up to the work he does in his PhD.
My research is on how to scale up and scale out, which are different concepts. Liquid extraction processes, which is a separation process to extract metals from a liquid solution, like for example aqueous solution into an organic solution. It's scale up and scale out are different concepts in the sense that scale up means making the equipment bigger with similar properties regardless of the size, and the scale out means parallelizing the system in the sense that whatever you do in one system, you can have many systems parallel doing the same.
So let's take a look at dimensional analysis in chemical engineering. So in this example, we will look at a spring. Elastic foundation is represented by a spring with a constant K. The spring rests on immobile ground and the movement of the mass before it reaches the spring is only governed by gravity. H is the height from which the mass falls, with the centers of masses aligned. The above information is only given to state our assumptions and to show how no other factors are affecting the movement of the mass. The function can therefore be defined by the following terms. We are now asked to find a relationship between the terms, and we will do so through the use of the Buckingham Pi theorem. We first have to establish the present dimensions, m for mass, L for length, and T for time, hence 3 dimensions. There are 5 variables x, h, k, g, and m, implying that there are 5 minus 3, 2 dimensionless groups. So we must now choose the repeating variables which must have ordered dimensions between them. For this specific example, we will choose m, the mass, g for gravity with units L over t squared, and k, the spring constant, with the units m over t squared. A simple product proves that these 3 repeating variables include all dimensions. So the first group, pi1, is given by x times m, the mass, to the power of a, times g to the power of b, times k to the power of c. Substituting in their dimensions will yield a set of equations which must equal to 0, allowing us to solve for a, b, and c. So through the use of linear algebra and simultaneous equations, we find b2 equal minus 1, c2 equal 1, and a2 equal minus 1, implying that pi1 can be defined as follows. We follow a similar process for the group pi2. However, in this case, rather than using x, we will proceed to use h. Here, we will solve for a2, b2, and c2, as follows. This yields a final answer for the group pi2. Now, we simply have to establish the relationships, which is that pi1 equals a function of pi2, or pi2 is a function of pi1, given that they are both dimensional. We now proceed to substitute in the functions that pi1 and pi2 equal to, yielding the final relations which are shown on screen. Thank you very much for watching this video.